Greetings of the day, dear students. In this video, we are going to discuss one important test on transformer, that is the open circuit test or no load test, and we will discuss its circuit diagram, how the meters are connected, voltmeter, ammeter and wattmeter, and which side the test is to be performed, whether it is to be performed on low voltage side or high voltage side, and what is the purpose of performing this test, right? And also we will see one example on this topic, right? We will discuss one example with the experimental data, how to calculate the different components we will see in this example, right? Coming to the open circuit or no load test, if you observe, this test is conducted on no load, right? High voltage winding is to be kept open. The high voltage, the transformer is going to have low voltage winding and high voltage winding. The key point is, while performing this test, the high voltage winding is to be kept open. That is, it is going to have no load on the high voltage side, right? Now whatever the meters, the ammeter, wattmeter and voltmeter are to be connected on the low voltage side, right? Of course, the voltmeter will be in parallel to the low voltage winding, and the ammeter is in series with the LV winding, and in this wattmeter, M indicates the main side, L indicates the load side, and C is a common point, and V indicates the potential voltage, right? So in this wattmeter MLCV, right, this indicates the current coil and this is the potential coil, right? Now here, this the main purpose of this test is to determine the no load loss or core losses, and also the no load current I naught, right? So if you observe, while performing this test, what happens is the normal voltage, the rated voltage will be applied. For example, if it is a some 115 by 230 volts, right? Now if it is on LV side, it is the rated voltage is 115 volts, right? The rated voltage will be applied on the LV side. Now even though there is no load on the secondary, still some small amount of current will be drawn by the transformer, right? Now that current will be some 2 to 10% of the rated value. That small amount of current will be 2 to 10% of the rated current. Now because of this current, no load current drawn I naught, some normal flux will be set up in the core, right? So hence the losses, whatever losses that occurs will constitute the iron losses, which will be recorded by the wattmeter. Now with respect to the core or copper losses, it is very negligibly small. Why? Because there is no load connected. Of course some small amount of current is drawn, right? And but the secondary is having no load, we can neglect the copper losses, which are negligibly small, and it is considered as nil in the secondary, because of the no load is connected on the HV side. Based on this, now whatever the wattmeter reads, that reading represents what? It represents the core loss under no load condition, right? Now the wattmeter, what does the wattmeter reads? It reads, it gives the reading, it gives the product of voltage across the potential coil, current flowing through the current coil, and cosine of the angle between the voltage and current. So indirectly the wattmeter W is equal to V1 I naught cos phi naught. Now once if you equate this value to the V1 I naught cos phi naught to the wattmeter reading, now easily we can calculate the cos phi naught. We know the wattmeter reading, and we know the voltage applied, we know the current drawn by the ammeter. So by using these 3 meter readings, we can calculate the cos phi naught. Once we know cos phi naught, we can calculate the phi naught. Based on that, we are now going to resolve the current I naught into two components. One is the magnetizing component I mu, and another one is the working component IW. So I mu is given by I naught sin phi naught, and working component is given by I naught cos phi naught, right? So here I mu represents the magnetizing component and IW represents the working component. Now already we know phi naught, already we know I naught, right? So based on that, the reactance x naught, the x naught value is given by V1 by I mu. Very, very important. The value of x naught reactance is given by V1 by I mu, and R naught is given by V1 by IW. So this is how, since the transformer is a no load, most of the times this I naught is almost equals to the I mu. This I naught is almost equal to the magnetizing component, right? So this is what all about the SC test, OC test. Now if you observe, let me consider a small example. Based on the test data, if you observe, if the no load test is performed, now the following data is obtained. The LV side voltage is 110 volts, HV side voltage is 220 volts, LV side current is 0.5 amps, low voltage side resistance is 0.6 ohm, and the wattmeter reading is 30 watt. Calculate magnetizing component of no load current and working component and iron losses, right? Dear students, number of times while discussing the problems I am repeating the same points. Whatever the data is given, based on the data, please represent the data with the help of proper variables. Once if you identify the proper variable for the given data, almost 50% of the problem is completed. Here in this context, low voltage winding LV side winding LV side voltage V1, it is to be represented with letter V1 equal to 110. High voltage side voltage represented with variable V2 equal to 220 volt. No load current represented with I naught 0.5. Wattmeter reading W equals to 30 watt. Now the question is, what about I mu and IW? Dear students, the wattmeter reads, what does it will read? V1 I naught cos phi naught. So we can calculate now cos phi naught. Wattmeter reading divided by V1 I naught. 30 divided by 110 into 0.5. It is 0.5454, right? Now the phi naught cos inverse of 0.5454. It gives you 56.94 degrees. What about sin phi naught? Sin of 56.94. It gives you 0.8381. Now I mu equals to I naught sin phi naught equals to 0.5, 0.8381, it equals to 0.419 amps. IW working component I naught cos phi naught, 0.5 into 0.5454, it is 0.2727 amps. Now what about copper losses? I naught square R1, I naught square R1, some small amount of copper losses will occur because of the no load current drawn by the primary, right? I naught square R1. So I naught square into R1, it is simply 0.15 watt. But the wattmeter is giving you the total losses because there is no load. Whatever the reading that is shown by the wattmeter, we can get with the help of that the iron loss equals to wattmeter reading minus copper loss, primary copper loss. So 30 minus 0.5 will give you the 29.85 watts or the iron losses, which are constant, which does not depend upon the load, whether it is on load or full load. These losses will be constant, right? 29.85 watt, right? So this is how we can calculate the losses and the no load current. Of course, sorry, I mu and IW from the given test data. Clear? Right. Thank you.